Yeah, good afternoon, class. I think we can start our session for today. So can I see that thumbs up if you can hear me okay? Okay, good. So before I start, again, any questions with regard to the subject matter that I presented last Tuesday or even module 1? Are there any questions? Okay, if there are none, I'm going to proceed with the material that I prepared for today. So today we're going to be discussing the bipolar junction transistor. We're going to be discussing it in more detail than you took up in EEE 123. What additional detail will we provide? Well, more details on its modes of operation. And we'll also be covering in more detail in this module the PNP transistor, because the PNP transistor was hardly touched upon in 123. Some of the material for the BJT was already introduced in module 1, and I'm the handler in charge of module 2, and I already published a video lecture as well as published the notes for this particular sub-module, the bipolar junction transistor. I published 2 lecture notes for this. One is on the BJT itself, on the models of the BJT, and the other is just a set of sample problems that are provided. So I'm not going to repeat the lecture that I already recorded. You can go through that. I'm just going to touch upon the parts that I think should be emphasized. Okay, BJT equations in active mode. So in my recorded lecture, I went through the derivation of the current equation for the BJT, that equation being IC is equal to beta times IB plus 1 plus beta times ICO, where beta is equal to alpha over 1 minus alpha, alpha being your common base large signal DC gain, common base large signal DC current gain. DC current gain. In particular, alpha is the percentage of emitter current that is collected at the collector. And we said that alpha is a number that is very close to 1. The closer that number to 1, the better your transistor. Okay, ICO we said was the reverse saturation current from collector to base with C to B reverse biased. So I also showed this. And ICO, being due to intrinsic carriers, is very small. That's of the range 10 to the minus 9 to 10 to the minus 15. Therefore, this particular quantity can actually be neglected. And we come up with a relationship between IC and IB, where we just say IC is equal to beta times IB. Okay, this is true for both the NPN and for the PNP transistor. Okay. Now, we normally use this together with the assumption that for silicon, VBE is approximately equal to 0.7 volts. So we use this equation together with this assumption that VBE is approximately equal to 0.7 volts to make DC calculations. Okay, for transistor circuits. In other words, when the signals in our transistor circuit are DC, are not time varying, okay, then we can assume this together with this. Okay, we derived and we did this last module. We derived an expression for I sub c in terms of VBE. So we said that I sub c is equal to I sub s e to the VBE over v sub t. So this is based on the Shockley model. The Shockley equation is applicable to a diode, to a p-n junction. So we know that the emitter current is proportional to e to the VBE over v sub t. That is Shockley's equation. So we assume here that the ideality factor is equal to 1 and that VBE is substantially large so that yung -1 is negligible. So we have IE proportional to e to the VBE over v sub t. Okay. However, in active mode, IC is proportional to IE. In fact, IC is equal to alpha times IE. Therefore, IC is also proportional to e to the VBE over v sub t. And the constant of proportionality we assign as the transistor parameter I sub s. IOS is what we call the transistor scale current. Okay. The reason why it's called the transistor scale current is because I sub s depends on the dimensions of the transistor. And this is also very, very small. I sub s typically would be anywhere from 10 to the minus 12 amperes to 10 to the minus 18 amperes. Okay, when do we use this? Normally, we use this when the signals applied to the transistor circuit are time varying. When the signals applied to the transistor circuit are time varying. So we have to be able to take into account the effect of changes, for example, in VBE with respect to IC. Here in DC calculations, usually because it's DC, then we assume that VBE is not changing. So we can assume it to be a constant. So we can use that to compute for all the other values in your circuit. But in time varying in transistor circuits with time varying signals, then we can assume that VBE will not be constant. Now note that this equation is for your NPN. Okay, for a PNP, all that will happen is your subscripts will be reversed. So you're going to get IC is now equal to I sub s e to the VEB over v sub t. So the voltage subscripts voltage subscripts. Are reversed. Okay. Remember that for a PNP, the directions of currents are reversed and the polarities of the voltages are reversed. Okay. Now, the way we handle that in this particular course, because the polarities of the voltages are reversed, you're going to be dealing with negative quantities. But we don't like dealing with negative quantities. It's not nice to deal with negative quantities. So instead of dealing with negative quantities, what we do is we just reverse the subscripts. So if in an NPN it's VBE, so that we don't have to deal with a negative quantity in PNP, we just use as reference VEB. So same thing for VCE, we're going to use VEC, and for VBE, for VBC, it's going to be VCB. So that's what we do. Okay, so here are our simplified active mode BJT models. So note, okay, what I have here is a controlled current source that forms my collector current. My controlled current source can either be a current-controlled current source, so that is beta being the control variable, or it can be a voltage-controlled current source, although this is now non-linear, where you use the exponential expression for I sub c in terms of VBE. So this is a current-controlled current source. The controlling variable is IB. This is a voltage-controlled current source. The controlling variable is this VBE. Again, when you use what, I already explained earlier. Usually one is used for DC calculations, usually, no? And then the other is used more for circuits with time varying inputs. Okay, so for the PNP, as I already explained, all the directions of currents are opposite. So IE will be inward, okay? And IB and IC will be outward. And then our polarities are reversed. Instead of VBE, you have VEB. So that this is now I sub S, e to the VEB over V sub t. And notice that the controlled current source will be now pointing in the opposite direction. Okay, I just want you to do this exercise just so that you get used to keying in the equation in your calculators. Okay, so it's a straightforward application of the formula. For an NPN transistor operating at 300 degrees Kelvin, you have your scale current equal to 10 to the minus 15 amperes. So assuming the transistor is in active mode, determine your collector current when your base to emitter voltage is 0.7. So can I ask you to just do this? It should take you just the time it takes to enter an equation in a simple equation in your calculator. And if you can send me your answer via chat. I'll go through the solution after I got a few answers through the chat box. So please go. Okay, I have a few answers that have come in. Let me wait for a few more. Be careful of your decimal points. You know? I'm getting some answers here. Well, yeah, okay. Yeah, it looks okay actually. Okay, I have enough responses. No? So what is the answer? Okay. The answer is I sub C is equal to 492.7 microamperes. Okay, I think it was introduced to you. So 1, 2, 3, yung engineering notation. If you wanted to be strict about it, every time you provide an answer in any of your engineering courses, you should use engineering notation. No? In engineering notation, your answer should always be a number between 1 and 999.99999, whatever, no? Multiplied by an exponent, and that exponent would be an engineering exponent, no? So it would be in the multiples of 3. No? So you have milli or micro or what have you. But I'm not going to be that strict about it. So this is for 492.7 microamperes. This is also equal to 0.492 milliamperes. No, so again, this is just a straightforward application of the formula. You have IC is equal to 10 to the minus 15 multiplied by E to the 0.70 over at 300 degrees Kelvin, our voltage equivalent of temperature is 0.026. Okay. Anyway, just okay, so this will give you these answers. So just as a refresher, V sub t, because not all the time will the problem given to you be at 300 degrees Kelvin. No? Sometimes it's going to be at a different temperature. Just remember that V sub t is equal to kT over Q. No? Where Q is the magnitude of the charge of an electron, K is Boltzmann's constant, and T is your temperature in degrees Kelvin. But this can be approximated by T over 11,600. So for example, 300 degrees Kelvin, if you divide it by 11,600, that gives you 25.8 millivolts or approximately 26 millivolts. So doon ang gagaling yung 26 millivolts. No? So you can actually use this to approximate the value of the thermal equivalent of voltage when it's a different temperature. No? So remember, this is your temperature in degrees Kelvin. Okay, so that's how we got the answer to letter A. Okay, if I raised my VBE by just 0.01 volts, okay, I'm going to get I sub C is equal to 723.7 microamperes. Or this is 0.724 milliamperes. Okay. So a difference in input voltage of 0.01, okay, resulted in a difference in current of 723 minus 492. That's about 200. What is it? No. That's right. $231 microamperes. No. So your IC increased by 231 microamperes. Now, what if what if that current was made to pass through a 10K resistor? So what if I sub C was made to pass through a 10K resistor? So this is just hypothetical. Okay. The voltage across the resistor will change by 231 times 10 to the minus 6, okay, multiplied by 10,000. Okay. So this is your 231 microamperes. This is your 10K. And what is that going to be equal to? That's going to be approximately equal to 2.31 volts. Okay. So I just wanted to illustrate that a 0.01 change in V sub VBE, okay, a 0.01 volt change in VBE is capable of creating a 2.31 voltage change across a resistor if that resistor is fed by a transistor, if fed by this transistor. And the reason why I wanted to point that out is this gives you a sense already that this can be used as an amplifier. Yung 0.01 na pagbabago, pwedeng maging 2.31 volts na pagbabago after passing through the transistor. So that gives you a sense that this can be used as an amplifier. And we're going to be taking up more of that in the next module, module 3, where where the transistor used as an amplifier will be discussed. Are there any questions with respect to that? Okay, so let me revisit the VI characteristic curves of your transistor. So when we talk about the characteristic curves of a BJT, that is a plot of your collector current versus your collector to emitter voltage. So this is VCE. This is if this is an NPN, or VEC if this was a PNP. So depending on whether it's an NPN or a PNP, that is what we have in our horizontal axis. Now, we have an additional parameter, that's IB. IB is treated as a parameter. This is a parameter of the plot. Okay, in other words, our plot will be for a particular value of I sub B. No. Let's say IB is equal to IB1. Then in active mode, IC will be equal to beta times IB1. So let's say this is my beta times IB1. That is the value of my beta times IB1. When will I be in active mode? I will be in active mode maybe in this particular region. So in this particular region, IC is a constant. It does not depend on VCE, and the value of IC will be equal to beta times IB1. So this is IB equal to IB1. Okay. And I am now here in active mode. As we reduce VCE, as VCE gets smaller, okay, expect that at some point, this current is going to drop. This current is going to drop. So it will look this way. No? Sorry about that. It will look this way. Okay, and this is what we call the onset of saturation. And for a silicon transistor, that will occur at VCE approximately equal to 0.3 volts. That happens at VCE approximately equal to 0.3 volts. Okay. At some point, your transistor is going to be what we call deep in saturation. And that will happen at about 0.2 volts. So this is, the transistor is deep in saturation. Okay. And in actual circuits, okay, in actual circuits, for as long as your emitter base is forward biased, VCE will not become smaller than this, no? Become smaller than this. In other words, hindi na bababa from 0.2 volts yung value ng VCE in actual circuits as long as your emitter base stays forward biased. I'm going to explain why later on, why it will not get smaller than 0.2 volts. So this is your active mode. And this area of operation, this is what you call your saturation mode. So we earlier learned that in saturation, both your emitter base and your collector base are forward biased. So you actually have a family of curves depending on the value of IB. So that probably is one curve. You'll have another curve this way. Okay. Another curve this way. So this corresponds to different values of IB. So this is IB equal to IB2. This is IB equal to IB3. In this particular case, you have IB1 would be greater than IB2, would be greater than IB3. And in all instances, in the active mode, your current is just equal to beta times IB. Okay, the question is this. Why does the collector current reduce when you go into saturation? Bakit bumababa yung collector current kapag nasa saturation na tayo? So I'm going to make reference to this to this figure, which is what we used. Okay, we use this figure in explaining the different current components in an NPN transistor. The difference now is I'm showing this figure in saturation. Notice that, okay, VBE forward biases the base emitter, and VBC forward biases the base collector. If this had been reverse biased, the current here would have been the opposite direction, and it would have been equal to ICO, your reverse saturation current. But because this is now forward biased, I'm going to get a forward current in the base to collector junction. I'm going to get a forward current in the base to collector junction, and that forward current is going to be due to diffusion. Remember that forward biased PN junction, the current is due to diffusion. So if I take a look at my collector current, my collector current is ICN minus IBC. I'm assuming now IBC is my forward bias current from my base to collector due to VBC. Okay, IBC. Now this is going to tend to reduce this, because IC is going to be this ICN minus this IBC. Kaya lumiliit yung value nung I sub C. So habang lumiliit yung value nung VCE, liliit ngayon yung value nung I sub C until we reach deep saturation. Okay. Now remember, in saturation, hindi na totoo to. Right? This was true when this current was approximately equal to 0, which is the case if this is reverse biased. But because this current is now substantial, this is no longer true. As a matter of fact, we can draw a new model. So what was our model in active mode? Our active mode model, okay, let's say we're using E as our reference node. So this is going to be my base. Between my base and my emitter, I have a diode. So this is my base to emitter diode. Okay. So this is my emitter. Okay. From my collector to my emitter, okay, my collector to my emitter, I have this component of current. This component of current from my collector to my emitter. And that component of current can be represented by my by my I sub S e to the VBE over V sub T. So this is now my collector. Now what about this component of current? This is from my base to collector. Okay. This component of current from Shockley's equation is going to be proportional to VBC. So I can actually write this as or model this as a controlled current source, okay, where the value of this source, let me call this ISC, scale current reference to the collector, e to the VBC all over V sub T. So as I increase the value of VBC, okay, naturally I will be increasing the value of IBC. So this is actually IBC. That is my current from my base to my collector. So originally this was open circuited because I had a very small reverse saturation current here. But now because this is forward biased, I have a current here, which will now tend to decrease the value of I sub C. So these are now my current components. Sorry, this is this way. I sub E. So this is my simplified saturation model. Okay, so when the saturation happens when your collector base starts becoming forward biased. Now it just so happens that the cut-in voltage of your collector base diode is about 0.4 volts. to 0.4 volts. This is the cut-in voltage of the collector base diode. So you might ask, di ba for silicon, we're talking about silicon here, no? Silicon. You might ask, di ba pag silicon 0.7? Well, 0.7 usually for well-constructed PN junctions. But the collector base is not a well-constructed PN junction. If you recall the typical construction of your NPN transistor, I have my N, no? That's my emitter. Then I have my P, which is my base. So this is my emitter. And then this is my base. So this is your planar construction. And then this is going to be another N region. And then this is my collector. So my emitter-based junction is this. But my collector-based junction is this. It's a much bigger area. If I mark out the collector-based junction, this is my collector-based junction. CB junction. It's a much bigger PN junction area. Okay, also subject to a lot of leakage currents, and in the boundaries of the junction, also surface currents. And if you take the net effect of that, it tends to make your cut-in voltage smaller. So your cut-in voltage is about 0.4 volts. And well into saturation, the value of your voltage across the PN junction goes up to about 0.5 volts. So let's take a look at how that is distributed. This is VBE. Okay. This is VBC. So this is VBC. And this is VCE. So note that VBE is equal to VBC plus VCE. This is by simple KVL. Okay. If we know that VBE is about 0.7, and we know that VBC is let's say nandito tayo 0.5. Okay. Then that means VCE will be 0.2 volts. And we call that VCE SAT. Okay. And if your transistor is a PNP, it's the same except that your subscripts are reversed. No? Instead of VBE, it's VEB. And then you have VCB and VEC. So dito sa kaliwa, it's VEB, okay, is equal to VCB plus VEC. Okay. And that will also give you 0.2 volts. So earlier I mentioned this voltage will not go, in practical circuits, this voltage will not go smaller than 0.2. What is the reason for that? Kasi itong 0.7, hindi nagbabago yan. Itong cut-in voltage ng base collector junction, hindi din magbabago sa 0.5. So ito, hindi din magbabago sa 0.2 ito. This will not change significantly from 0.2 under these conditions. Okay. What if I apply VBE greater than 0.7? No? Or what if I apply VBC greater than 0.5? If you take a diode, and you apply a voltage, let's say you apply a voltage where V is greater than 0.7, what do you expect to happen to this diode? No? First of all, based on what you learned in Triple E 123, this is an invalid circuit. No? Because here you have a voltage V, here you have a voltage of 0.7. No? Let me redraw that. No? Medyo magulo yung drawing ko. Okay? So if I have this voltage V, I put this across a diode. So V is forward biasing the diode. If the diode is forward biased, V sub D is approximately equal to 0.7. So what if V is greater than 0.7? What if V is greater than 0.7? So from 1 to 3, I just mentioned this is what is considered an invalid circuit. Why? This is greater than 0.7, this is 0.7. So how can you have two voltages in parallel of different values? But what will happen in reality? In reality, if you try to do this, okay, you are pushing the operating point of the diode very high in its characteristic curve. If you remember the characteristic curve of the diode, okay, this is the characteristic curve. If I try to increase V sub D further, I am pushing my operating point way up here. No? Very, very high. In other words, my current is going to be very, very high. What do you expect to happen pag masyadong mataas yung current? Anyone? Anyone? What will happen, no, if my current is very high?
Masisira po yung component, sir.
Exactly, no. You're going to destroy your component, no, because your component has a power rating. It can only dissipate a certain amount of power. For example, if my diode is 1 watt, then that means the maximum current that my diode should be able to carry is 1 watt divided by 0.7, which is just a little over 1 ampere. If I put a larger voltage, it will create a much bigger current, and my diode will not be able to dissipate the power. The diode will just burn, will just get destroyed. So that's also what's going to happen if you try to apply voltages greater than 0.7 across your base emitter, 0.5 across your collector base. Now, usually in an actual transistor circuit, you're going to have resistances that will limit the value of the current that flows. And in those cases, you protect your junctions. But just the same, these are going to end up being the junction voltages, and your VCE SAT will never really stray very much from 0.2 when your transistor is deep in saturation. So this is now the simplified saturation mode BJT models. This is for an NPN, and this is for a PNP. For your NPN, again, this is for purpose of DC calculation. Your base emitter, you approximate that to be 0.7, and if you know that your transistor is in saturation, your collector emitter will be about 0.2. For a PNP, your emitter base, take note, baliktad yung subscripts, will be 0.7, and your emitter collector will be 0.2. These are large signal models. So usually you use these models in making DC calculations. Okay, so again, no, this is just for purpose of you exercising your fingers with your calculators. Can you solve this problem? Can you tell me what the value of VCE is going to be when VBE is 0.7? So assume that the transistor is in active mode. No? Assume that the transistor is in active mode. So again, please answer through the chat box. Any answers for letter A? Just for letter A, no? Letter A lang. Okay, I have some answers coming in. This is yeah, I have okay. Let's wait for a couple more, no? Okay, so sorry. Yeah, okay, I think I have enough answers, no? Most of you got it right. Okay. When VB is equal to 0.7, actually we already computed for the current that will flow. So actually this is the same transistor that I used in my first example. So given the value of VBE, you can compute for the value of I sub C, assuming it's in active mode, no? In the first example, I didn't provide a value for VCC. I just said assume it's in active mode. In this particular case, this is immaterial if we know that it is in active mode. The 10 volts is immaterial if we know that it is in active mode. And you can compute for I sub C. And we already said earlier that that's 492.7 microamperes. So what is VCE? VCE, we just apply a KVL to this particular path. In other words, applying KVL, we start at 10 volts. 10 volts minus the drop across this resistor, which is IC times 10K, minus the drop across the transistor, which is VCE, will give me 0, which is my ground. No? That's how I apply KVL along this path. So that's 10 minus the drop across the resistor, which is RC times IC, minus VCE will be equal to 0. And I'm going to get VCE consistent with the answers of most of you in the chat box is about 5.07 volts. Okay. Now, what about when VBE is equal to 0.71? So using the same formula, okay, I'm going to get VCE is equal to 2.76 volts. 2.76 volts. So you recall what I said earlier? Yung 0.01 change in VBE now produces a 2.31 volt, tama ba? 5.07, yeah, 2.31 volt change in VCE. No? So, ang liit ng change dito sa VBE, 0.01, ang laki ng change dito sa VCE. No? Which means that if this is time varying, no, changing very small, this will also be time varying but changing very large. No? That's why we said that this can be an amplifier. Okay, let's check VBE equal to 0.72. At VBE equal to 0.72 volts, I'm going to get IC is equal to, no, assuming my Shockley model, no, IC is equal to, I have it somewhere here, 1.063 milliamperes. No? This is assuming active mode. Let me try to compute for VCE. No? VCE is equal to 10 minus RCIC. Lo and behold, I'm going to get negative 0.632 volts. This is a negative number. First of all, taking a look at the circuit, saan magagaling yung negative voltage dito? No? My voltage here is positive 10. My lowest voltage here is 0. It doesn't seem right that I will have a voltage somewhere in between that is negative, no? Because I'm going from 10 here all the way down to 0. So I expect as I go from 10 to 0, my voltage is decreasing, no? But this indicates that from here to here, my voltage is increasing. So it actually, if you already have a feel for these values, you're already going to see that there's something wrong with this. Because why will I have an increasing voltage from this point to this point? No? But what is this? This is indicative. First of all, no, your VCE is not greater than VCE SAT. Right? We said that to be in the active region, if you take a look at this, to be in the active region, the value of VCE should be greater than VCE SAT. So that's either 0.3 volts at the onset of saturation or 0.2 volts if you consider deep in saturation. So ibig sabihin yan, we're already here, somewhere here in the saturation region. So yun yung sinasabi rito. Hindi kagaya dito, no? In both these cases, VCE is greater than VCE SAT. Remember, no, you know that your transistor is in active mode if VCE is greater than VCE SAT and your base emitter is forward biased. Now we know that this is forward biased, okay? Because our base emitter voltages are positive. In fact, it is in all cases greater than the cut-in voltage of the diode, of the base emitter diode. So most likely the base emitter diode is conducting. So your base emitter we know is forward biased. Now in this particular case, VCE is greater than VCE SAT, so we know that the assumption here is active is correct. No? So the conclusion here is the transistor is already saturated. Wala na siya dun sa active region. So having said that, what will be the value of VCE? What is going to be the value of VCE? Anyone? Just shout it out. What will be the value of VCE? Yeah, I have an answer from someone. Yeah. This is just going to be VCE SAT. Right? So we can assume that under these conditions, your transistor is going to be deep in saturation. VC is going to be equal to VCE SAT. Okay. So the takeaway here is this, no? Whenever you compute for your value of collector current, make sure you always check your assumption. Siguraduhin nyo that you always check for your assumption. I'm going to shift to the example problems that I gave. I'm not going to go through it in detail, but let me just go through it very quickly. Sorry. So that is here. No? Okay, so this is part 4X. These are just BJT sample problems. I provided this to you so that you have a feel for solving BJT circuit problems with DC. No? These are all DC solutions or DC computations. Okay, so in the analysis of BJT circuits, and you already learned this in EEE 123, okay, you have to apply the correct model of your BJT, and that model depends on the operating mode of the BJT. If you do not know the operating mode, usually we start with the assumption that the BJT is in active mode. And then we can use this relationship, IC is equal to beta times IB. So that this is if you don't know the operating mode. But you have to validate. You always have to validate. Now, how do you validate? There are two ways of validating whether it's in active mode. First of all, the emitter junction has to be forward biased. Actually, that's true for both active and saturation. The emitter junction has to be forward biased. If the collector junction is reverse biased, you know it's in active mode. The other way is you compare VCE to VCE SAT. In the case of a PNP, it's VEC that you compare to VEC SAT. No? So depending on whether it's an NPN or a PNP. Again, the assumption here is the emitter-based junction is forward biased. If VCE is greater than VCE SAT, then you are in active mode. Otherwise, you know that you are in saturation mode, and you have to use the saturation model. And the simplified saturation model is just your 0.2 volt source. No? Pag sinabi sa inyo it is only at the onset of saturation, then it's going to be a 0.3 volt source. So the example problems that I gave here, well, we already went to a similar problem like this. So this is just using the exponential model. This time, the base current being given, okay, and you being asked to determine what the base emitter voltage is using the exponential model. So first, it requires you to determine the collector current. So from the base current, you can determine the collector current using IC equal to beta IB. And from the collector current, you can now get the base to emitter voltage using the exponential model of your transistor. Okay. But remember, you made an assumption here that the transistor is in the active mode. So that has to be validated. That has to be validated. Okay. And the way it was validated here was the value of VBC was computed. And we showed that VBC, this is the sorry, this should be no. this is the collector to base junction. We show that VBC is negative, meaning to say that the collector to base junction is reverse biased. So it validates that it's in active mode. The other way is by computing for VCE. If we show that VCE is greater than VCE sat, then we can also say that the transistor is in active mode. So that's the first example. So the second example is the same problem, just now asking you what range of currents will the transistor be in saturation. Okay. Now the next example, I put this in because I wanted you to have a practice problem, or I wanted to show you a sample problem where the transistor is a PNP transistor, because you had very little experience computing for voltages and currents in PNP transistor circuits in 1, 2, 3. So note that when the transistor is a PNP transistor, we usually draw the emitter up and the collector down, because like I said earlier, we don't want to deal with negative values of currents, and we also have to reverse the subscripts because we don't want to deal with negative values of voltages. Okay? So yung mga subscripts natin, lahat dapat i-reverse. So in this particular case, for example, instead of computing for VCE, we compute for VEC. And then the other thing that I wanted you to experience is, what if you have multiple power supplies? So notice that you have a separate power supply connected to your emitter resistor, and a different power supply connected to your collector resistor. If you take a look at what this looks like in an actual circuit, well, all it is you actually have a voltage here, which is 10 volts, reference to ground. And here, you also have a voltage which is 10 volts. Okay, so 10 volts. But this time, the positive terminal is the one referenced to ground. Okay. In the fourth example, still a PNP transistor with a dual supply. Okay. This time with your base terminal grounded, so you're asked to compute for all the voltages and currents, in your transistor circuit. And finally, the fourth example, the fifth example, where I don't provide the solution, I'm going to ask you, I'm asking you to solve this on your own. In this particular example, this is a circuit which combines a PNP and an NPN transistor. So you're supposed to solve for VC1, IC1, IB2, and IE2. Okay, this problem actually I picked up from Cedra and Smith microelectronic circuits. There's a solution to this problem in Cedra and Smith, but in solving this problem, Cedra and Smith made this particular assumption that IB2 is very much smaller than IC1. Itong IB2 is very much smaller than IC1, so that it can be neglected. It can be neglected. Okay, that's a fair way of solving the problem, because in actual circuits, your parameters are not exact anyway. For example, beta being 100 might be what the data sheet says, but the actual beta might be 5% off, depending on the tolerance of your transistor. So because your parameters are not exact, in actual life, if you do this for a living, in actual life, you're allowed to make assumptions. And this is a very valid assumption. But what I want you to do when you try to solve this problem is, I want you not to make this assumption. In other words, I want you to get an exact solution to the problem. And I gave here the answers. Okay, so try solving this without making this assumption. So that's all I wanted to discuss for this afternoon's session. So again, no, if you haven't gone through the recorded lecture, go through that first, and then go through this. This will emphasize certain points in that lecture. No, if you're having problem solving the example 5, I offer that if you send me your solution, I will tell you what's wrong with it if you're not coming up with the answers that are indicated in that particular example. Okay. Any questions? Any questions? So that's all. We ended up a bit earlier than we usually do. I will close the session as soon as the last person leaves. Thank you.
Thank you, sir.
Thank you,
Yeah,
po, sir.
you're
Thank you,
welcome.
sir.
You're welcome. You're welcome.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you po, sir.
Thank you, sir.
You're welcome. You're welcome.